Bismillahirrahmanirrahim. Assalamu alaikum students. Today we are going to discuss the last topic of chapter 6, which is system design activities from objects to subsystems. So what is system design? So system design consists of transforming the analysis model into design model. So we have to discuss system design activities today. So as we have already discussed in chapter 5, section 5.4, that how we generate objects from use cases. We discussed in chapter 5, heading 5.4, analysis of activities from use cases to objects. In that section, we have discussed various activities involved while transforming from use cases to objects. Now, in today's lecture, we are going to discuss how we can generate, how can from objects we identify subsystems. So, three points we are going to discuss today. First, we will make analysis model for a route planning system, which is our case study for today, with the name MyTrip. Second is we identify design goals, and third is we identify subsystems. So what is the purpose of today's lecture? We are going to identify subsystems from our analysis model. So system design activities from objects to subsystems. System design consists of transforming the analysis model, and analysis model we have already discussed in chapter 5 into design model that takes into account the non-functional requirements described in requirement analysis model. So we start with the analysis model for MyTrip. So MyTrip is the example case study which will help us in understanding that how we identify subsystems from objects. Then we describe the identification of design goals. First, we generate analysis model for MyTrip from the use cases. Then, after making the analysis model, we describe the we identify design goals, and after that we identify the initial subsystem decomposition for this example case study. So as I told you in the previous slide, what is our first step? To generate objects from the use cases, or to generate analysis model from the use cases. So the main use cases of MyTrip, which is a route planning system for car drivers, is plan trip and execute trip. So let me discuss this use case. And the flow of events of planned trip is the driver activates her computer and logs into trip planning web service. Now in this use case, I will identify objects with the help of activities we have already discussed in chapter 5. So the driver activates her computer and logs into trip planning web service. The driver enters constraints for a trip as a sequence of destination. So destination can be a target for object. So the same object can appear in multiple use cases, but you have to write in your analysis model that object just once. So based on database of maps, the planning service computes the shortest way of visiting the destination in the order specified. So the result is a sequence of segments. So segment can be object, a series of crossings. Crossing can be object, and list of direction. Direction can be object. So driver saves the planning trip by name in the planning service database for later retrieval. Next main use case in the route planning system is execute trip. After the driver plan the trip, now next step he will execute the planned trip. So the driver starts her car and logs into the onboard route assistant. So the driver specifies the planning service and name of the trip. The board route assistant obtain the list of destinations, direction, segment, and crossing from the planning service. Now we have identified following objects from the use cases, and we on the basis of that we obtained the following analysis model. So in the analysis model for MyTrip, these are the objects. So route assistant, trip, planning service, direction, crossing, segment, destination, and location. And this line represents the association between them. So in this slide, the description of each of the identified element of the model is described, like what is crossing. So crossing is a geographical point where several segments meet. Destination represents a location where the driver wishes to go. Given a crossing and an adjacent segment, a driver describes in natural language how to steer the car onto the given segment. So this you can say table tells us the description of each identified object. So a trip is a sequence of directions between two destinations. So next is during requirement elicitation, the client specified the following non-functional requirements for MyTrip. So the non-functional requirements of MyTrip is: MyTrip is in contact with the planning service via a wireless modem. Once the trip has been started, MyTrip should give correct direction even if modem fails to maintain a connection with the planning service. So MyTrip should minimize connection time. Replanning is possible only if the connection to the planning service is possible, and planning service can support at least 5 different drivers and 1,000 trips. So what is our next step? Our next step is to identify design goals based on the non-functional requirements specified by the client. The analysis model and non-functional requirements for MyTrip is there. So the next step in system design, you can say the identification of design goals is the first step of system design. So next step is to identify design goals for MyTrip. So design goals identify the qualities that our system should focus on. So these design goals we can infer from non-functional requirements. The non-functional requirements we got in previous slide, or from application domain. That which non-functional requirement is you have to incorporate for a particular domain. You must have to incorporate for a particular domain. So the following box summarizes the design goals we identified for MyTrip, keeping in view the non-functional requirements from the previous slide as well as the application domain. So design goal for MyTrip is, first is reliability. So MyTrip should be reliable. So as you know what reliability is. Second is fault tolerant. That MyTrip should be fault tolerant to loss of connectivity with the routing service. So this requirement, this non-functional requirement, we have specified in the previous slide, which is number 2 non-functional requirement. Once the trip has been started, MyTrip should give correct directions even if modem fails to maintain a connection with the planning service. So keeping in view that non-functional requirement, we inferred following design goal. So then security we deduce from the application domain, as numerous drivers will have access to same trip planning server. And modifiability, that MyTrip should be modifiable to use different routing services, as this is a design goal, as we want to provide the ability for drivers to select a trip planning service of their choice. In general, developers need to prioritize that which design goal is more important to the project, and usually they have to trade off against each other. So because it is unrealistic to develop a software that is safe, secure, and at the same time cheap as well. So the table below lists several possible trade-offs. First is space versus speed. That if you want to increase the speed or response time of a software, you require more memory for it. So if the software does not meet memory space constraints, data can be compressed at the cost of speed. So if you want to increase the speed, you have to occupy more space. So so there should be a trade-off between them, that which design goal is more important for the problem at hand. So deliver time versus functionality. So if development runs behind schedule, project manager can deliver less functionality than specified on time. So if the time to deliver a software is there, so the project manager can deliver with less functionality. So again there should be a trade-off between them, that if you want to achieve this, if you want to achieve to deliver the software on time, you have to compromise on you may have to compromise on some functionality. So the next is delivery time versus quality. That if the time to hand over the software to client is there, then project manager can deliver the software on time with known bugs without completing the testing. So if you want, again there is a trade-off, if you want to achieve this, you have to compromise on this. Or if you want to achieve high quality, you have to compromise on delivery time. So again, next is delivery time versus staffing. So if development runs behind schedule, project manager can add resources. So usually adding resources if you are adding resources to your project at a later stage, it usually decreases productivity, because you have to train them or brought them up to date. So you have to compromise any of them. So the next step in system design is to identify subsystems. So finding subsystems during system design is similar to finding objects during analysis. So so that's why we can use the same heuristics which we used to identify objects during analysis. These heuristics we already discussed in chapter 5. So subsystem decomposition is a constantly revised whenever new issues are addressed. So several subsystems are can be merged into one subsystem. Complex subsystem can be split into parts. So whenever a new issue is addressed, it results in the change in the it can result in the change of the subsystem. The initial subsystem decomposition should be derived from the functional requirement. So from functional requirement we can determine what the initial subsystem decomposition for our project. So in addition, following heuristics for subsystem identification is to should also be kept in mind. The first is assign objects identified in one use case into the same subsystem. That in one use case, if we identified 4 objects, that we should keep them into the same subsystem. So second is create a dedicated system for objects used for moving data among subsystems. So the objects that are involved in the movement, in the data movement between subsystems, there should be a dedicated subsystem for that, so that any change in that should not affect the subsystems. Third is minimize the number of associations crossing subsystem boundaries. This is related with low coupling between subsystems, and all objects in the same subsystem should be functionally related. This is associated with high cohesion. For example, in the MyTrip system that we are discussing, we identified 2 major groups of objects, one related with plan trip use case and other related with execute trip use case. So we identified 2 subsystems. One is planning subsystem, in which and the classes trip, planning service, direction, destination, segment and crossing. We assigned these classes to planning subsystem, and the remaining we assigned to routing subsystem based on the functionality of these classes. So the subsystems should be in a way that there will be low coupling between them, and they would be highly cohesive. So the responsibility of planning subsystem is it is responsible for constructing a trip connecting a sequence of destinations, and routing subsystem is responsible for downloading a trip from the planning service. So the responsibilities of both subsystems are given over here. So first we identified objects from the use cases, and then we identified design goals from the non-functional requirements as well as from application domain, and in this third step we are going to identify subsystems on the basis of objects we identified already. So subsystem decomposition reduces the complexity of this solution domain by minimizing coupling among subsystems, as the subsystems should be identified in a way that the coupling between them should be low. So the facade design pattern allows to further reduce dependency between classes by encapsulating subsystem with a simple unified interface. So to further reduce complexity, we use facade design pattern. So basically facade design pattern hides the complexity of the system and provides an interface to the client using which the client can access the methods of the subsystem. So let me show you the UML class diagram depicting facade design pattern. So the figure shows the compiler class here is a facade hiding the classes code generator, optimizer, parse node, parser, and lexer. So the facade provides access only to public services like create, generate, parse tree, only to public services offered by this subsystem, and hide all the unnecessary details. By doing this, coupling will be reduced. So basically the purpose of here the compiler acts as a facade. So and it is basically an interface that is provided to the client using which the client can access the public methods of subsystem classes. So this type of pattern comes under structural pattern, as this pattern adds an interface to existing system to hide its complexity. So the pattern involves a single class which provides simplified methods required by client and delegate call to methods of existing system classes. So by encapsulating subsystem with facade design pattern that provides an interface to client using which the client can access the functionality of the subsystem, the complexity of the system will further be reduced. So these subsystems identified during initial subsystem decomposition often result from grouping several functionality related classes. So these classes, lexer, code generator, optimizer, parser, are functionally related to each other. So by doing subsystem decomposition, we are grouping the functionally related classes together. So these subsystems are good candidates for facade design pattern, and then by using facade design pattern they are encapsulated under one class. So in this way complexity will further be reduced. Summary of today's lecture is we have discussed system design activities from objects, that we are moving from objects to subsystems. So in chapter number 5 we discussed the activities that are involved while we move from use cases to objects. Now in today's lecture we have discussed activities while we move from objects to subsystems. So for that we took an example of MyTrip, which is a route planning system for car drivers. So initially we, on the basis of use cases, we generated an analysis model for MyTrip. After that we identified various design goals for MyTrip, in keeping in mind the non-functional requirements that are specified by client. So after identifying design goals, the next step is to identify subsystems. So we have identified subsystems for MyTrip, keeping in mind various heuristics for grouping objects into subsystems. So by identifying subsystems, the complexity of the system will be reduced. So then we further discussed encapsulating subsystems with facade design pattern. So facade design pattern allows us to further reduce dependency between classes by encapsulating a subsystem with a simple unified interface. Now you can access the subsystem functionality only through that interface. So that is all for today's lecture. Thank you.